Greetings, this is Mrs. Radigan with a lesson on power functions. Here's a quick video that does a good job of introducing them.
I want to introduce the idea of a power function. A power function is one of the form y equals x to the n, where n is any real number constant. A lot of our parent functions are actually power functions. For example, y equals x, one of our simplest functions, is a power function where n is 1. So here n equals 1. Y equals x squared, obviously a power function, n equals 2. Y equals x cubed, n equals 3, also a power function. Y equals 1 over x is a power function. Here, 1 over x is the same as x to the negative 1. So this is a power function with n equals negative 1. And finally, y equals the square root of x. The square root of x is the same as x to the 1/2. So this is a power function with n equals 1/2.
We're going to add another component of the power function called k. This is called the constant of variation. So a power function has the form of f of x equals k times x to the a, where k and a are not 0. The constant a is called the power. In the video he called it n, but we're calling it a. And the k is the constant of variation. So we say that f of x varies as the 8th power of x, or f of x is proportional to the 8th power of x. When we have positive powers, we have direct variation. When we have negative powers, like x to the negative 2, we have inverse variation. Let's take a look at our first example, which is writing a power function from some words. So it says that from empirical evidence and laws of physics, it's been found that the period of time t for the full swing of a pendulum varies as the square root of the pendulum's length. So we're going to write that such that the period of time t as a function of length equals some constant of variation times the square root, because it varies as the square root of the pendulum's length, or k equals L to the 1/2. In the next example, we're going to look at some power functions and analyze their power, constant of variation, and various other attributes. So in the first one, we have the cube root of x, which we can write as 1 times x to the 1/3. So the power is 1/3 and the constant of variation is 1. If we look at the graph of that, we can see that it is going in the x direction from negative infinity to infinity, and the same for y. That means that this function is continuous at all values of x. And if we look at the increasing and decreasing, it is constantly increasing, so it's increasing for all of its x values. It is symmetric about the origin if we flip it over the y-axis and then the x-axis, so that means it has odd symmetry. It is not bounded on either side, above or below. It also has no extrema, mins or maxes. And then if we look at the ends of the graph, we see that as x goes to negative infinity, it is going down. So we would call that the limit as x approaches negative infinity of the function goes to negative y, or negative infinity. And then if we look at the right side here, as x goes to positive infinity, it is going up. So the limit as x goes to positive infinity of the function would be positive infinity. Now let's look at 1 over x squared. So we have rewrite that as 1 times x to the negative 2. We could call that a power of negative 2 and a constant of variation of 1. If we look at this graph, we can see that our domain goes from negative infinity, but then it's approaching 0, and we have a vertical asymptote there, and then we skip over 0 and then keep going after that to infinity. So our domain would be negative infinity to 0 and 0 to infinity. Our range, it doesn't quite get to 0, and it goes up to positive infinity, so it would be 0 to infinity. We see that the discontinuity here is that vertical asymptote at x equals 0, so it's discontinuous at x equals 0. And then we talk about where it's increasing and decreasing. So it's increasing on this interval, so negative infinity to 0, and then it's decreasing on this interval, so 0 to infinity. It is reflected across the y-axis, so it has even symmetry. And it is bounded below, but not above. It has no local extrema, so no mins and maxes. It does have those horizontal asymptotes, so it's approaching 0 here, and it has a vertical asymptote there. So it has two asymptotes, one horizontal one at x equals 0 and one vertical one at y equals 0. And then the end behavior, so as we're looking at the left side here, as x is going to negative infinity, we see this value is approaching 0, but not quite getting there. And then the same is true for the right side. As we go to positive infinity, it's approaching 0, but not quite getting there. In this next slide, we see all the attributes, same attributes, but for x cubed. So domain, range, continuity, increasing, decreasing, symmetry, bounded, extrema, asymptotes, and end behavior. And in these examples then, if we look at these functions, it's just asking us to describe the graph given the parent function and sketch it by hand. So if we know that x cubed looks like this, we would just vertically stretch 2x cubed by 2. So the original function would be flatter than the stretched function. So the original one would be the dotted line. The stretched one would be the black line, so it goes up faster. In the next one, we have negative 2/3 x to the fourth. So the parent function of x to the fourth looks like this dotted blue line. It kind of has a wiggle here. But then if we throw a constant of variation of negative 2/3 on the front, we know that's a vertical shrink of 2/3 and a reflection across the x-axis. So it's going to widen out a bit and get reflected across the x-axis. In this next slide, we're going to talk about the attributes k and a and how they affect the graph. So when you have a positive constant of variation, you're going to have functions that lie in quadrant 1. If you have a negative constant of variation, you're going to have functions that lie in quadrant 4. So if we look here, we can see that all of these have a k value of 1. So something that has an a value, so an exponent of 1, would be just a line. Something with an exponent that is between 0 and 1, like a square root, would look like this blue function. Something that has an exponent bigger than 1, like this red, like x cubed, would look like this. And something that has a negative exponent would be decreasing, because that would be 1 over x squared. So the bigger x got, the smaller the y value would get. That's if k is positive. So that would be the coefficient on all the x's. If you put a negative coefficient on those, you're just going to flip those all over the x-axis because that would be a vertical reflection. So we just take all those same functions. So those would be like negative x to the negative 2, negative x cubed, negative x, and negative of x to the 1/2. The other thing we can learn about the function in general is that we have one of the following three things when x is less than 0. So when we have a domain value that is negative, essentially. If we have something like a square root or a fourth root, we have a function that is undefined. So it doesn't actually enter in to the negative x value. So it would not be in quadrant 2 or 3. If we know that the function is even, so if we had a k value that was positive and the function was even, it would just be reflected across the y-axis. So we would get like a U shape, or we would get two, for the green one, we'd get two of these shapes. So we would just get all these shapes reflected across the y-axis. If we have an odd function, then we're going to take these and we're going to reflect them across the origin, so they would lie over here in quadrant 3. If it was a negative k, they would lie over here in quadrant 2. So with that in mind, let's take a look at some of these functions and see if we can identify some key attributes given the k value and the a value. So this one has a k value of 2. That's greater than 0, so we know that that is going to be in quadrant 1, and it's going to pass through the point 1, 2, because if we plug a 1 in here, that's going to be 2 times 1. So 1, 2 would be a point on the graph. We also know that the a is negative, so that is going to mean that our x values are undefined at 0, because that would be 1 over 0, which we know is undefined. And this negative is also going to, negative 3 is going to make it an odd function, so it would be reflected across the origin, and the function would be decreasing, so it would look something like this. So it passes through 1, 2. It is in the first quadrant, and it's odd, so it's reflected across the origin. In this next example, we have negative 0.4 as our k value, so that value is less than 0, which means our function is in quadrant 4. It's going to pass through 0.1, comma negative 0.4. Our a value is 3/2, so that means that our function is going to be undefined for negative x values, because we'd be trying to take the square root of a negative. It is going to be decreasing because of that negative k value. And if we look at the graph of that, it's just going to look like this. It's passing through 1, negative 0.4. It's in that quadrant 4, and it's decreasing. And it's undefined over in the negative x values. The next one, negative x to the 0.4, our k value is negative 1. So our graph is going to contain that 0.1, negative 1, and it's going to be in that fourth quadrant since k was less than 1, which makes our function decreasing. It is even because that is an exponent of 2/5. So if we look at that graph here, we see that our function is in the fourth quadrant, reflected across the y-axis because it's even, and contains the point 1, negative 1. This slide right here just gives us all the attributes of the square root function. And then in our last example, we are going to use some data to create a power function model. In this case, it is orbital period as a function of distance from the sun. So we have distance from the sun as our x value and our orbital period as our y value. We're just going to enter those into the calculator. So here I'm going to go to Stat Edit, enter those x values and those y values. Then to find the function, I'm going to click Stat Calc. I want the power model. So I'm going to go to Power Regression A, hit Enter. My x values are in L1, my y values are in L2. I want to store that using the vars yvars function y1. And I'll run that regression, and there's our power model. So given that regression values of 0.2, that's our constant of variation, and then the b value of 1.5, that is our exponent. We see that this has an r-squared value of 0.99, so it has a very strong relationship. And then the last thing it said for us to do is predict the orbital period for Neptune, which is 4,497 GMs from the sun. So we're going to go ahead and do second y equals. We're going to turn our plot on, make sure L1 and L2 are selected, and then we're going to hit zoom 9, and we should see our points and our function there. But we need to check our window. It looks like our x max is not big enough, so we're going to change that to 4,500. Regraph it, and then if we want to predict a y value, we're going to use second trace value. We're going to type in our value of 4497, and we're going to get our predicted y value of 60,150 days for that period. So that would be about 165 years, which is the value given in the National Geographic.